हैं? Hello, students. Good afternoon to all of you. Welcome back to L&T College Multimedia Studio. Today's lecture is focused on Werners experiment for modern coordination chemistry. Okay. So in the previous lectures, what I have discussed about the coordination chemistry, that was actually basic outline, basic overview. But today's we will reach in detail to elaborate the chemistry of coordinations in a metals, and how the metals and ligands actually they have interacted to each other to form a particular coordination compounds. So for this purpose, so Werners, actually Alfred Werner, who is a eminent and first inorganic scientist, you can say, in 1913, he has got a Nobel Prize for the discovery of coordination chemistry, right? So as you know that most of the elements in the periodic table, actually they are all metals, and all metal nearly forms coordination compounds, right? So how the coordination chemistry actually came into existence, so that is elaborated by the Alfred Werners. And the history of the coordination compounds actually came into existence through the deep studies in 1866 to 1913. So in this period, actually 1866 and this is 1913. So this is the period in which Alfred Werners actually spent his time to for the evolution of modern coordination chemistry, and ultimately in 1913 he got Nobel Prize. Okay, so actually all the metals actually nearly forms complex compound. So in his experiment, actually Alfred Werners, what he has actually taken and try to do experiment is he has taken cobalt chloride, right? So cobalt chloride, that is COCl3, and another reagent he has taken ammonia, right? So this is ammonia. So once the react this cobalt chloride, COCl3 plus NH3, right? So what Werners did, he has actually tried to react this COCl3 with ammonia to form, that is COCl3 dot NH3. So this is a adduct type chemical structure, so that he got in his experiment. Okay, so this is actually normal compound, normal salt, you can say, and this is ammonia. So once these two reagent react each other to form this type of chemical adducts, where N is the variation number. So N is equal to either it may be 1, 2, 3, like that. So the main inferences of this chemical adduct is that he found COCl3 6NH3, right? The first compound that he has selected, and he has obtained, that is COCl3 6NH3, and second compound, that is COCl3 into 5NH3, and third compound COCl3 into 4NH3, and fourth compound, that is COCl3 into 3NH3. So these are the four compounds actually Werners found in his experiment. So here this compound and this compound, this compound, this compound. Here 6NH3, 5NH3, 4NH3, 3NH3. But he did not get 2NH3 or 1NH3 in the separation of the compounds after the reaction of cobalt chloride and ammonia. So from these compounds, what kind of actually inferences he reflected? So that will be like that. So once he has separated this CO, Cl3, 6 and H3, right? So here cobalt is the transition metal, so that exists actually in the +3 oxidation state. But in the further to explain the actually behavior of this adduct, he has actually used another reagent, that is actually silver nitrate. Okay, and that silver nitrate so is used to uh, explain the behavior of this kind of chemical adducts. So what happens? In excess, he has added AgNO3, right? So what happens? Here CO, here you can see, so this is like that. So here 3 Cl minus means it is precipitated as 3AgCl. So get precipitated, right? So in the aqueous solution of this compound, silver nitrate was added as a result of precipitation of 3 chloride ion. So from this particular structure, so from this precipitation, he has actually confirmed that these chloride ions are outside of the coordination sphere. So as in the previous lectures, I have actually suggested you that what is coordination sphere, and so coordination sphere actually contains metal and that is associated with ligands. So it means that CO NH3 and that is Cl3. So the precipitation of 3 chloride ion confirms that the structure of this coordination compound is like that. So in the coordination sphere, cobalt is directly connected to ammonia molecule. So here 6, right? And the outside of the coordination sphere, so this is actually 3 chloride ion, right? So what is inferences here? So this exists as CO NH3 whole 6, and here 3 plus or here 3 Cl minus, right? So this 3 Cl minus confirms that the coordination sphere, or this is complex ion, and this is called complex ion, right? So this complex ion bears 3 positive charge, and in outside as a counter ion there is 3 chloride ion. So that is why this 3 chloride ion gets precipitated as 3AgCl. Okay, so after adding this AgNO3, this ammonia actually this is ammonia did not react with silver nitrate, did not reacted. with silver nitrate. Okay, so that confirms that ammonia molecule is directly bonded to cobalt metal, but the chloride ions, actually they get precipitated through the ammonia, right? So this is outside of the coordination sphere. So the ultimately he has got the structure like that. So this is cobalt NH3 का whole 6, okay, and this is 3 plus and this is 3Cl minus. So from this structure, so this is complex cation and this is anion. So a type of coordination compound, or it is ionic coordination compound. So this means this is a cation and this is anion. You're looking like NaCl. It means in NaCl, that is Na plus and Cl minus. So 1 plus charge is satisfied by 1 negative charge on the chloride. So it is a type of general salt or normal salt. So this is a type of coordination salt or complex salt. So these 3 plus on the coordination sphere, actually it is has one significant meaning, and another number is that is in the coordination sphere, that is 6. So plus 3 and 6, so they are very important number in the complex chemistry. So what indicates plus 3? So this indicates plus 3 primary valency, right? So this is primary valency, and what 6 indicates, that is secondary valency, right? So primary valency is associated with oxidation number, right? So this is oxidation number of the metal, okay, and this secondary valency is associated with coordination number. It means this compound actually exists as CONH3 whole 6, that is Cl3 outside of the sphere. So this is the real structure of the coordination compound, and here primary valency of this cobalt is plus 3. That means this cobalt bears plus 3 charge, and the total number of ammonia molecules that is surrounded to cobalt ion, that is 6. So this indicates the coordination number is 6. So for this structure, coordination number is 6. This is Cn. Cn means coordination number is 6 and primary valency is plus 3. So on the basis of formation of this type of chemical structure, he has elaborated that this compound has primary valency, that is plus 3, which indicates the oxidation number of the cobalt, and number of ammonia molecule is 6, that indicates the coordination number of the metal that is surrounded with 6 ammonia molecules. So this is the experiment of Werner on cobalt chloride with ammonia. Okay, so what another inferences he has got, and on the basis of precipitation of chloride ion, it means that is once this cobalt NH3 ka whole 6 Cl3, once there was added in excess, this is what happened, this is in excess AgNO3. So what he has got, that is CONH3 whole 6 3 plus 3Cl minus. Here total number of ions is 4. So after the reaction of silver nitrate with this compound in aqueous solution, he has got total number of ions, that is 4. So that is one type of ion is like that, complex ion, and 3 chloride ion. That is total number of ions is 4. Okay. So another physical parameter that he has elaborated, electrical conductance, right? Electrical conductance. So electrical conductance, as you know that, as the number of ions in aqueous solution increases, the electrical conductivity of the solution increases. So this particular complex compound furnishes one complex cation and 3 chloride ion. It means there is 4 number of ions. So this 4 number actually indicates that the electrical conductivity of this solution is high. So on that basis also he has actually elaborated the structure of this complex ion. Okay, so here 4 ions. And another experiment, so as the total number of ions are 4, so high electrical conductivity for this compound. Okay. Another physical parameter that he has actually added, that is cryoscopic measurement. Cryoscopic measurement. So that is cryoscopic constant, that is Kf. So this is actually expressed as delta Tf is equal to Kf multiply molality. This is molality. So larger the value of molality, greater will be depression in freezing point. So actually this cryoscopic measurements is associated with colligative properties, and colligative properties depends on the number of the particles in a solutions. So here in the aqueous solution, the number of particles means the number of actually ions was found for this compound, that is very high, that is 4 per formula unit. Per mole of formula unit there is 4 particles. So larger the value of molality, mole per kg, m, that is molality means mole per kg, right? So larger the value of mole, so greater will be depression in freezing point. So for this compound there was observed little high depression in freezing point. So these are the experiment, so that was actually carried out by the Werners in the experimental laboratory, and he has postulated that the compound possesses actually um, two type of valency, that is primary valency and other one is secondary valency. So primary valency is ionizable. So you can see that this 3 Cl3, that is ionizable, right? And secondary valency is non-ionizable. So ammonia molecule which are present in the coordination sphere, it is not ionizable, and this is ionizable. And another aspect what he has actually expressed here, so that is CONH3 का whole 6 Cl3, that is secondary valency is non-ionizable, but it is directional, right? So the structure that was predicted like that, 6 ammonia molecule, so that was actually H3N, H3N, NH3, NH3, right? And one up of the plane and another down of the plane. right? And so dotted line Cl, Cl, Cl. So this chloride cobalt dotted line indicates primary valency, right? So primary valency, and this cobalt ammonia bond, this is solid bond, solid line indicates secondary valency, right? So because of the precipitation of the chloride ions, so they are electrostatically interacted by the cobalt cation. Okay, so this is expressed as dotted line, but the bonds which are strong and stable, they are expressed in the solid line. Okay, so 6 ammonia molecule, they are directly bonded to cobalt, so that is expressed as solid line, so that confirms the secondary valency, and which are non-ionizable, and the 3 dotted lines actually expressed primary valency. So each complex compound or coordination compound actually possess coordination number, and that is secondary valency, and it is primary valency. So primary valency depends on the oxidation number of the metal. So on the basis of oxidation number, the complex compound may be positive, negative, or neutral, right? So complex ion may be either positive, so positive complex ion, or it may be negative complex ion, or it may be neutral. So it will depends on the primary valency. So if the primary valency is actually 0 on the coordination sphere, it means that cobalt exists as 0 oxidation state. Okay, so uh, these are the experiments actually for a particular compound he has elaborated. So this has yellow color, right? So yellow color, okay. So the compound what he has separated actually bears yellow color, okay. And on the basis of this experiment, he has actually tried to uh, elaborate and uh, revolute the coordination chemistry, and they came into existence for the modern coordination chemistry, and for the discovery of such type of experiment he has got actually Nobel Prize in 1913. Okay, so this is the way the coordination chemistry came into revolution, and for modern as a modern coordination chemistry. So thank you for this lecture.